Welcome to the series of e-learning modules on problems, formulation, solution by graphical method, Simplex algorithm, Charnes M technique. Coming to the introduction, graphical method. Problem 1. Use the graphical method to solve the following linear programming problem. Maximize z is equal to 2x1 plus x2 subject to constraints. First one, x1 plus 2x2 is less than equal to 10. Second, x1 plus x2 is less than equal to 6. Third, x1 minus x2 less than 2. Fourth, x1 minus 2x2 is less than equal to 1 and where x1, x2 is greater than equal to 0. Solution 1. Coming to step 1. State the problem in the mathematical form. In this case, the problem is already stated in the mathematical form. Step 2. We shall treat x1 as the horizontal axis and x2 as the vertical axis. Each constraint will be plotted on the graph by treating it as linear equation, and it is then that the appropriate inequality conditions will be used to mark the area of feasible solutions. Consider the constraint x1 plus 2x2 less than or equal to 10. Treat this as the equation x1 plus 2x2 is equal to 10. The easiest way to plot this line is to find any 2 points that satisfy the equation and then to draw a straight line through them. The 2 points are generally the points at which the line intersects the x1 and x2 axis. For example, when x1 is equal to 0, we get 2x2 is equal to 10 or x2 is equal to 5. Similarly, when x2 is equal to 0, x1 is equal to 10. These 2 points are then connected by a straight line as shown in the figure. But the question is, where are these points satisfying x1 plus 2x2 is lesser than or equal to 10? Any point above the constraint line violates the inequality condition, but any point below the line does not violate the constraint. Thus, the inequality and non-negativity condition can only be satisfied by the shaded area, that is the feasible region. Similarly, the constraints x1 plus x2 is less than equal to 6, and if we take x1 is equal to 6 and x2 is equal to 6 in the second equation. In the third equation, x1 minus x2 is equal to 2 and we get x1 is equal to 2 and x2 is equal to minus 2 in the third equation. In the fourth equation, x1 minus 2x2 is equal to 1 and we get x1 is equal to 1 and x2 is equal to minus half. Here we may note that we have considered that are below the lines for the negative values of x2 because the non-negativity condition x2 is greater than equal to 0, which implies that the negative value of x2 are not desirable. All the 3 equations are plotted on the graph and are indicated by the shaded area O, A, B, C, D, E. Since the optimal value of the objective function occurs at one of the extreme points of the feasible region, it is necessary to determine their coordinates. The coordinates of extreme points of the feasible region are O is equal to 0, 0, A is equal to 1, 0, B is equal to 3, 1, C is equal to 4, 2, D is equal to 2, 4 and E 0, 5. Evaluate objective function value at each extreme point of the feasible region as shown in the table. The first column is the extreme points O, A, B, C, D, E and coordinates 0, 0, 1, 0, 3, 1, 4, 2, 2, 4 and 0, 5. The third column shows the objective function value. So, for the first coordinate O 0, 0, we get the objective function is equal to 0. The second coordinate a10, the objective function value will be 2. The third coordinate b31, the objective function value will be 7. The fourth coordinate c42, the objective function value is 10. The fifth coordinate d24, the objective function value is 8, and the last coordinate e05, the objective function value is 5. Since we desire z to be maximum, from the table we can conclude that the maximum value of z is equal to 10 is achieved at the point extreme C42. Hence, the optimal solution to the given linear programming problem is x1 is equal to 4, x2 is equal to 2 and max z is equal to 10. Coming to problem 2. GJ Breweries Limited have two bottling plants, one located at G and the other at J. Each plant products 3 drinks, that is whiskey, beer and brandy, named A, B and C respectively. The number of the bottles as shown in the produced per day are shown in the table. Drink, whiskey, plant at G 1500 and plant at J 1500. Beer, plant at G 3000 and plant at J 1000. Brandy, plant at G 2000 and plant at J 5000. A market survey indicates that during the month of July, there will be a demand of 20,000 bottles of whiskey, 40,000 bottles of beer and 44,000 bottles of brandy. The operating cost per day for plants at G and J are 600 and 400 monetary units. For how many days each plant has to run in July so as to minimize the production cost while still meeting the market demand? Solve graphically. Coming to the solution. Step 1. State the problem in the mathematical form. Let us define the following decision variables x1 and x2 is equal to number of days at plant G and J respectively. Then the LP model of the given problem can be expressed as minimize z is equal to 600 x1 plus 400 x2 subject to the constraints. Firstly, 3x1 plus 3x2 is greater than or equal to 40. Second, 3x1 plus x2 is greater than or equal to 40. And third, 2x1 plus 5x2 is greater than or equal to 44 and x1, x2 greater than or equal to 0. Step 2. We shall treat x1 as the horizontal axis and x2 as the vertical axis. Each constraint will be plotted on the graph by treating it as linear equation, and it is then that the appropriate inequality conditions will be used to mark the area of feasible solutions. Consider the constraint 3x1 plus 3x2 greater than or equal to 40. Treat this as the equation 3x1 plus 3x2 is equal to 40. The easiest way to plot this line is to find any 2 points that satisfy the equation and then to draw a straight line through them. The 2 points are generally the points at which the line intersects the x1 and x2 axis. For example, when x1 is equal to 0, we get 3x2 is equal to 40, x2 is equal to 13. Similarly, when x2 is equal to 0, 3x1 is equal to 40, x1 is equal to 13. These 2 points are then connected by a straight line as shown in the figure. But the question is, where are these points satisfying 5x1 plus x2 is greater than or equal to 10? Any point above the constraint line violates the inequality condition, but any point below the line does not violate the constraint. Thus, the inequality and non-negativity condition can only be satisfied by the shaded area, that is feasible region. Similarly, the constraints 3x1 plus x2 is greater than or equal to 40, and by solving we get x1 is equal to 13 and x2 is equal to 40 in the second equation. In the third equation, 2x1 plus 5x2 is greater than or equal to 44, and we get x1 is equal to 22 and x2 is equal to 8 in the third equation, and all the three equations are plotted on the graph and are indicated by the shaded area as shown in the figure. Since all the constraints have been graphed, the area which is bounded by all the constraints lines, including the boundary points, is called the feasible region or solution space. The feasible region is shown by the shaded area ABC. Since the optimal value of the objective function occurs at one of the extreme points of the feasible region, it is necessary to determine their coordinates. The coordinates of extreme points of the feasible region are A is equal to 22, 0, B is equal to 12, 4, C is equal to 0, 40. Evaluate objective function value at each extreme point of the feasible region as shown in the table. The first column is the extreme points A, B, C and coordinates 22, 0, 12, 4 and 0, 40. The third column shows the objective function value. So, for the first coordinate A, 22, 0, the objective function value will be 13,200. The second coordinate B, 12, 4, the objective function value will be 8,800. The third coordinate C, 0, 40, the objective function value is 16,000. Since we desire Z to be minimum, from the table we can conclude that the minimum value of Z is equal to 8,800 is achieved at the point extreme B, 12, 4. Hence, the optimal solution to the given linear programming problem is x1 is equal to 12 days, x2 is equal to 4 days and minimum Z is equal to rupees 8,800. Now coming to problem 3. Solve the following linear programming problem using the penalty big M method. Minimize Z is equal to 5x1 plus 3x2. Subject to the constraints, 2x1 plus 4x2 is less than or equal to 12, 2x1 plus 2x2 is equal to 10, 5x1 plus 2x2 is greater than or equal to 10 and x1, x2 greater than or equal to 0. Coming to the solution. Introduce the slack variable S1, surplus variable S2 and artificial variable A1 and A2 in the constraints of the given linear programming problem. The standard form of the linear programming problem is stated as follows. Maximize Z is equal to 5x1 plus 3x2 plus 0s1 plus 0s2 plus ma1 plus ma2. Subject to the constraints, 2x1 plus 4x2 plus s1 is equal to 12, 2x1 plus 2x2 plus a1 is equal to 10, 5x1 plus 2x2 minus s2 plus a2 is equal to 10 and x1, x2, s1, s2, a1, a2 greater than or equal to 0. An initial basic feasible solution is obtained by letting x1 is equal to x2 is equal to s2 is equal to 0. Therefore, the initial basic feasible solution is x1 is equal to 12, a1 is equal to 10, a2 is equal to 10 and min z is equal to 10m plus 10m is equal to 20m. Here, it may be noted that the columns which correspond to the current basic variable and from the basis, that is identity matrix, are S1, that is slack variable, A1 and A2 both artificial variables. The initial basic feasible solution is given in the table. Initial solution: Cj is equal to 5, 3, 0, 0, m, m. The coefficient of basic variable CB is equal to 0, m, m. Variables in basis is B are S1, A1, A2. The solution values B is equal to XB are 12, 10, 10. The variables X1 are 2, 2, 5. The variables X2 are 4, 2, 2. The slack variable S1 are 1, 0, 0. The surplus variable S2 are 0, 0, minus 1. The artificial variable A1 is 0, 1, 0 and A2 is 0, 0, 1. Since the value C1 minus Z1 is equal to 5 minus 7m is the smallest value, therefore X1 becomes the entering variable. To decide which basic variable should leave the basis, the minimum ratio is calculated as 12 by 2, 10 by 2 and 10 by 5, which is nothing but xb by x1. Zj is calculated by multiplying the x1 variable and the coefficient and taking their summation. So, in the x1 column we will get 0 into 2 plus m into 2 plus m into 5 is equal to 7m. Similarly, we will get the Zj values of the other column as 4m, 0 minus m, m and m. In the next row, we calculate the values of Cj minus Zj, which is equal to 5 minus 7m, 3 minus 4m, 0, m, 0 and 0. Coming to iteration 1. Introduce variable x1 into the basis and remove a2 from the basis by applying the following row operations. The row solution is shown in the table below. R3 new is to R3 old by 5. R2 new to R2 old minus 2R3 new. R1 new to R1 old minus 2R3 new. Then we get the new table with the following values. The coefficient are 0, m and 5. The variables in basis are S1, A1 and X1. The solution values are 8, 6 and 2. The Cj values are the same. The values of X1 variable are 0, 0 and 1. The values of X2 variable are 16 by 5, 6 by 5 and 2 by 5. The values are S1 is 1, 0 and 0. The S2 values are 2 by 5, 2 by 5 and minus 1 by 5. The values of A1 are 0, 1, 0. The minimum ratio is 8 by 16 by 5, 6 by 6 by 5, 2 by 2 by 5. The values of Z are 10 plus 6m. The values of Zj are 5, 6m by 5 plus 2, 0, 2m by 5 minus 1 and m. The value of Cj minus Zj 0, minus 6m by 5 plus 1, 0, minus 2m by 5 plus 1 and 0. Coming to iteration 2. Introduce variable x2 into the basis and remove s1 from the basis by applying the following elementary row operations. The new solution is shown in the table. R1 new to R1 old x5 by 16. R2 new to R2 old minus 6 by 5 R1 new. R1 new to R3 new minus R3 old minus 2 by 5 R1 new. We will get the table with the following values. The coefficients are 0, m and 5. The variables in basis are S1, A1 and X1. The solution values are 5 by 2, 3 and 1. The Cj values are the same. The values of X1 variable are 0, 0 and 1. The values of X2 variable are 1, 0 and 0. The values of S1 are 5 by 16, minus 3 by 8 and minus 1 by 8. The S2 values are 1 by 8, 1 by 4 and minus 1 by 4. The values of A1 are 0, 1, 0. The minimum ratio is 5 by 2 by 1 by 8, 3 by 1 by 4. The values of Z are 5 plus 3m. The values of Zj are 5, 3, minus 3m by 8, m by 4 and m. The values of Cj minus Zj are 0, 0, 3m by 8, minus 5 by 16, minus m by 4, plus 7 by 8 and 0. Coming to iteration 3. Introduce S2 into the basis and remove A1 from the basis by applying the following new operation: R2 new to R2 old x4, R1 new to R1 old minus 1 by 8 R2 new, R3 new to R3 old plus 1 by 4 R2 new. We will get the table with the following values. The coefficients are 3, 0 and 5. The variables in basis are x2, s2 and x1. The solution values are 1, 12 and 4. The Cj values are the same. The values of x1 variable are 0, 0 and 1. The values of x2 variable are 1, 0 and 0. The values of S1 are 1 by 2 minus 3 by 2 and minus 1 by 2. The S2 values are 0, 1 and 0. The values of A1 are minus 1 by 2, 4 and 1. The value of Z is 23. The values of Zj are 5, 3, minus 1, 0 and 7 by 2. The values of Cj minus Zj are 0, 0, 1, 0 and m minus 7 by 2. From the above table, it is observed that all Cj minus Zj is greater than or equal to 0. Thus, an optimal solution has arrived at which value of variables as x1 is equal to 4, x2 is equal to 1, x1 is equal to 0, s2 is equal to 12 and min z is equal to 23. Coming to problem 4. An air force is experimenting with 3 types of bombs P, Q and R, in which 3 kinds of explosives, that is A, B and C, will be used. Taking the various factors into account, it has been decided to use the maximum 600 kg of explosive A, at least 480 kg of explosive B and exactly 540 kg of explosive C. Bomb P requires 322 kg, bomb Q requires 143 kg and bomb R requires 423 kg of explosive. Bomb P is estimated to give the equivalent of a 2-ton explosion, bomb Q a 3-ton explosion and bomb R a 4-ton explosion respectively. Under what production schedule can the Air Force make the biggest bang? Coming to the solution 4. Let x1, x2 and x3 be the number of bombs of type P, Q and R to be experimented respectively. Then the LP model for the problem is written as: maximize Z is equal to 2x1 plus 3x2 plus 4x3 subject to the constraints: first, 3x1 plus x2 plus 4x3 less than or equal to 600. Second, 2x1 plus 4x2 plus 2x3 is greater than or equal to 480 and 2x1 plus 3x2 plus 3x3 is equal to 540 and x1, x2 and x3 is greater than or equal to 0. Introducing slack, surplus and artificial variables to convert the LP problem into its standard form as follows. Maximize Z is equal to x1 plus 3x2 plus 4x3 plus 0s1 plus 0s2 minus ma1 minus ma2 subject to the constraints. First, 3x2 plus x2 plus 4x3 plus s1 is equal to 600. 2x1 plus 4x2 plus 2x3 minus s2 plus a1 is equal to 480. Third, 2x1 plus 3x2 plus 3x3 plus a2 is equal to 540, and x1, x2, x3, s1, s2, a1, a2 is greater than equal to 0. The initial basic feasible solution is obtained by setting x1 equal to x2 equal to s2 equal to 0. The initial solutions are s1 equal to 600, a1 equal to 480, a2 equal to 540. Max Z is equal to minus 1020 m, and the obtained solution is shown in the table. Again, from the table we can see the C2 minus Z2 value in x2 column is the largest positive, entering variable x2 to replace basic variable a1 into the basis. For this, apply the following row operations. R2 new is equal to R2 old into 1 by 4, that is the key element. R1 new is equal to R2 old minus R2 new. R3 new is equal to R3 old minus 3 R2 new. To get the new solutions, we have prepared the new table as shown. In this table, C3 minus Z3 value in x3 column is largest positive. Enter variable x3 to replace the basic variable a2 into the basis. For this, apply the following row operations. R3 new is equal to R3 old into 2 by 3 key element. R1 new equal to R1 old minus 7 by 2 R3 new. R2 new equal to R2 old minus 1 by 2 R3 new to get the new solution. As shown in this table all Cj minus Zj is less than equal to 0, and artificial variables a1 and a2 have been reduced to 0. Thus, an optimal solution has been arrived with x1 is equal to 0 bombs of type P, x2 is equal to 60 bombs of type Q, x3 is equal to 120 bombs of type R at largest benefit of Z is equal to 660. Coming to the summary. Here's a summary of our learning in this session. To understand the importance of using CPM, knowing the CPM network techniques. Thank you.